Okay, so thanks a lot for the invitation, and it's great to be here to give a talk. Yeah, the title of my talk is quite vague because I thought about two subjects I could talk about, and both can be described by this topic. And I think I'll try to squeeze a little bit from both of them. Yeah, we'll start by something that some of you might have already heard. So first application of this whole kind of way of thinking will be to confine subgroups of semi-simple groups. Maybe, what should I say? Like the whole idea here will be to use probabilistic methods to study some properties of discrete subgroups of semi-simple groups. Sometimes when you add some, you construct some probabilistic structure, depending on your subgroup, you find some kind of dynamics that you can play and you couldn't have played before, and this helps proving some stuff about our subgroup. So first application will be to confine subgroups in higher rank, and probably this will take today's lecture and half of tomorrow's lecture. Yeah, whenever I say something which is not clear, please ask questions. So, yeah, we'll start. In notation is written here, so this notation will not change throughout the talk. We'll always be working with real semi-simple group G. K will be the maximal compact subgroup, which is unique after conjugation. P will be the minimal parabolic, also unique after conjugation. And inside them, we choose a maximal split torus. We also have unipotent radical of P, denoted N. Yeah, and sometimes you'll see that I use letter X for the symmetric space, which I identify with the coset space G mod K. The only thing we need to remember about this space right now is that it comes with a canonical left G invariant Riemannian metric. And we write letter D for the induced metric on X. And this metric will be pulled back to G where it becomes a semi-metric, which is still left G and right K invariant. So now I can define what a confined subgroup is. Sorry? No. If you in blue you have examples of what they mean for PGL3, and that's it basically. If you understand it for PGL3, it's too small.
I don't know. Can everyone see the blue? The blue is almost invisible to me.
Because of the light. Yeah. Okay.
I chose a bad seat. Maybe it's a fine for everyone.
No, you're right. It's like if I look at it from here, I also don't see anything.
Yeah. If you can't see the blue, find a way to see the blue.
Yeah, maybe when they will become relevant, I will write examples. It's not necessary to know structure theory of semi-simple groups, just some properties, and all of them are already visible, will be visible in those examples. Right. So let me define what a confined subgroup is, and this definition makes sense for any locally compact second countable group. G, we don't have to assume it's Lie group. So a subgroup lambda inside G is confined if there exists a bounded set W, which contains identity, such that the intersection of any conjugate of lambda by G, so this is by definition G inverse lambda G, intersected with W is more than just identity. So it's not equal to identity. Or maybe I can write it contains, but it's not equal. Okay, so there will always be some element other than identity in this set.
The quantifier on G is.
And this is for every G in G. So no matter how you conjugate your group, you still keep seeing non-trivial elements in some bounded set. So for this definition to be truly interesting, we will assume that our G has no center. If it has a center, then every subgroup containing a non-trivial central element would be confined. So just, I feel it's simpler to discuss this concept when G is center free. So from now on, assume that center of G is trivial. So this is why I chose PGL here, not SL. Okay. Okay, so examples of such groups are always provided by lattices. And actually, we were supposed to give exercises. So this will be an exercise. 2. Normal subgroups of lattices, so non-trivial. Yeah, and let me just say that in rank 1, I won't give you details, but in rank 1, we can find many examples which are not of the form 1 and 2. Okay.
By that, you're alluding to things like convex or compact groups, or?
Convex or compact, they're almost never, well, if they're not lattices, they're never confined because you can walk into the funnel.
Okay.
Okay, there is a job, maybe, if you're familiar with locally symmetric spaces, there is a nice geometric interpretation of being confined. So lambda is confined. This is equivalent to saying that this locally symmetric space, X mod lambda, has a bounded injectivity radius, uniformly bounded. Which means that no matter where you are on this quotient, so it can be infinite, but no matter what point you take, if you try to draw a large ball around this point, after some radius, uniformly bounded radius, you will start to see overlaps. So it means that you can kind of, within bounded radius, you can witness that you are on a proper quotient from every part of the space. So this is the situation that happens in the confined case, and this question about a convex or compact case, we will then see something like this, and then funnel. So here the injectivity radius will be bounded, but this part, if you go there, injectivity radius grows, and it stops being confined. So this is not.
Like what happens for some C covers?
Certain surfaces have Z covers, and that's
The reason for that is that you can repeat the Lassant construction by wobbling the generators a bit. You can still use ping pong to show that it's a discrete subgroup, but it's no longer contained in a lattice, but that kind of it will be confined. Okay.
sometimes there are no Z covers.
Yeah, sometimes there might be no Z covers. This is all still true for rigid rank 1 groups which have no Z covers. It is this construction. I wouldn't say it's easy, so it would be an exercise with star. But you can read Lassant's paper about the fact that every lattice in real rank 1 has a normal subgroup of infinity next, and modify the construction so that you get confined subgroups which are not contained in any obvious lattice. Maybe provably not contained in any lattice. Yeah. Okay. Yeah. So those are some examples, and you'll see that in higher rank, all 2 and 3 do not really apply, because in higher rank we have Margulis normal subgroup theorem, which says that a normal subgroup of a lattice is either finite index, so it's also a lattice, or it's contained in a center, which in this case would be trivial. So 2 doesn't provide any new examples. And perhaps motivated by this, Margulis conjectured that in higher rank, non-trivial confined subgroups are always lattices. So let me erase this beautiful example. Okay. Okay, right. So, yeah, it's an extension of normal subgroup theorem in some sense. But the original proof of normal subgroup theorem doesn't apply here. We have no quotients to work with. Okay, so now I should use those buttons.
Yeah, they can get really angry if you don't use the button.
If I don't use them. Oh, it's okay. If I listen to the opening, presentation, I would know that. But there was no. Okay, so this is T1. Okay.
I think you have to hold it or you press it.
No, it doesn't. Not that easy. Oh no! This is not the. Wait, what? Oh, I'm confused. This should lower and. Okay, yeah.
Yeah, you just went down one to T2.
Of course, yes. Also, this number refers to the order in this direction.
Yes.
Okay. Oh, of course.
T is for tableau. It all makes sense.
Yeah. Okay, so with Sahig Galander in a recent work, we showed that this conjecture is true. Yes, Margulis was right. I think many theorems could be stated like this. And there is a version for a product of rank 1 spaces, rank 1 groups, but I want to keep things simple. So we'll stick to the simple higher rank case. And the proof is, so what's the idea of the proof? So we will start with something which is confined and discrete. Maybe assume it's not a lattice, or maybe not. Well, just confined and discrete. And well, we would like to use some higher rank dynamics to study this group. But the problem is that if we just look at the quotient or something like this, we have no obvious finite measure. So it's hard to use traditional dynamical arguments. But using certain suitably chosen random sampling of the conjugates of our group will construct a new system on which we will be able to use higher rank dynamics. So, yeah?
So maybe you said that when you're using a confined subgroup, are you assuming that lambda is discrete?
Yes, lambda is, yeah.
Is this should be in your definition of confined, or?
Actually, you know what? This definition does not need lambda to be discrete. It just needs to be closed. Sorry?
You can take G as lambda.
I could take G.
You can take any subgroup containing a lattice, right? Like some.
Yeah, you're right. Oh yeah, okay. So what you know what? I could add a discrete assumption to Margulis' conjecture, but this table is like this blackboard is so high that I'll add it here. And this is discrete always. Oh. Okay. Yeah.
So the conjecture is if lambda is a discrete confined subgroup, then it's
Yes. Thank you. Yeah. There are subgroups which are closed, like random. You can, for example, take a closed parabolic subgroup, or ordinary parabolic subgroup, and it's also confined using this definition here. But yeah, whenever I say lambda, I will mean a discrete subgroup, and Margulis' conjecture is for discrete subgroups. Yeah. Maybe. Okay. Right. Okay, so for the proof, we'll need to work with the space of all subgroups of G. And this will be the space sub G, which is defined as just the space of all, maybe I'll write H so that it's clear, H in G, where H is a closed subgroup. And the topology on this space will be the topology of Hausdorff convergence on bounded subsets. We put it a little bit higher, just D1. And well, I will just write in plain words. What does it mean? So if I have a sequence lambda n converging to lambda in sub G, then this means that the following two things happen. So for every epsilon bigger than 0, for n big enough, I have the following containment. And every bounded W. If I intersect lambda with W, this is eventually contained in epsilon thickening of lambda n. So I just multiply lambda n by b epsilon, and conversely, the intersection of lambda n with W is contained in lambda times b epsilon. And this is just ball of radius epsilon. In G. Right, so any point of lambda should be approximable by points of lambda n, and conversely, nothing else should be approximable. So, yeah, let's, what else can we say about this space? So, yeah.
Is the word big enough depend on W, or is it independent of W?
Epsilon and n, sorry, n can be, yeah, n will depend on W. So I should write this, every W, this holds for big N. Yeah.
But for all W, there exists a big N.
Yeah. So N was depending on W and epsilon. So if this topology sub G is a compact metrizable space, it's called Chabot topology. And G acts continuously by conjugation. So I will use this notation, lambda G is equal to G inverse lambda G. Okay. So inside this space, we'll distinguish the subspace of discrete subgroups. Those will be the groups we're most interested in. And a word of warning. So this subspace is not closed. So for example, if I define my sequence of subgroups like this, so there will be, this will be inside SL2. Then this lambda T, as T gets bigger, this conjugation by those elements squeezes the copy of Z. And this group converges in this Chaboty topology to just a real unipotent subgroup. And if we, for example, if we converge, if we took sequence of t that go to -infinity, we would get a trivial subgroup. So this happens as t goes to +infinity. The picture is like this. Sequence of dots which get kind of more and more dense will converge eventually to a full line. And if you kind of consider this situation like in a more detailed way, you can actually show that this is the only way, one of two ways in which you can get a non-discrete limit as limit of discrete groups. So let me put some exercises that are related to this. Oh yeah, no, I wasn't supposed to do this. Let me move it back and then use this.
I'm not sure moving it backwards. Can you move one down at the same time that you move the one up?
I don't think so. No, it stops. But okay, if I push two buttons at the same time, everything stops working. Okay, so I wanted to put, I think, T2 down. Yeah. So yeah, I'll give you two exercises about this. One, I mean, we already had one exercise. But I won't number them. I'll prepare a list in PDF to show at the exercise session. So you can show that if lambda n converge to lambda and all lambda n's are discrete, then maybe better to write H. Then the connected component, H0, is solvable. And two, and this will actually be useful for us, show that lambda is confined if and only if one is not in the closure of its orbit inside sub G. So the trivial subgroup is not in the orbit closure. Okay, and this characterization, it's not hard. It's basically unraveling the definition of what confined means. With no, this is correct. So, oh yeah, sorry. Of course, in, yeah, not in. Yeah, not in. Thank you. Yeah, so this is, you take definition of confined and what convergence in Chaboty topology means, and you'd be getting that exactly. Right.
And that's important. Like, it's very important when it's discrete for that.
Actually, no. For that, no. For that, no. This holds, even if this would hold even for non-discrete groups. Because, well, if your starting group is not discrete, then you have no chance of getting anything confined, at least in Lie groups, because you always have this chunk going from, tangent to the Lie algebra, and you cannot kill it by conjugating away. It's related to the fact that Grassmannians are compact, so there is no escape of mass. You cannot conjugate the subspace to infinity. Okay, so this is important because this allows us to attack this original problem by showing that, well, basically we have to show that if lambda is a subgroup of higher rank group, discrete subgroup, then, well, if it's not a lattice, we must see one in the closure of its orbit. This is like purely a dynamical statement. And soon we'll build some measures with which will allow us to show this. Okay. So there's one more thing we need to understand about this space because before talking about stationary random subgroups. So what should I erase? What is the oldest? This one is the oldest. T1. No. Yeah? I'm not sure. I'm not sure. It's possible that you can show unipotent. Nilpotent, which would be stronger. I just wasn't 100% sure, so I left it as solvable. Okay, T2 goes up. So one nice thing that happens for higher rank groups and more generally for groups which are do not contain a SL2 factor is that in this space of subgroups, if you are close enough to a lattice, you have to be a lattice. So we'll prove it for G higher rank. At some point I'll just indicate where to modify the proof to get it for a bit larger family of groups. So if G is simple higher rank, and lambda in G is a lattice, so G, then any lambda in sub G close enough to gamma is also a lattice. Okay. So lattices are somehow, well, they're not exactly isolated, but they're rigid. Okay. So I think it's nice to see the proof of this lemma because it also illustrates how the topology works in the space. I think I need some colors. Okay, but let me now write the proof. Okay, so we start by choosing a generating set for gamma. And we also choose a finite set of relations. So those relations will be just, I guess, subsets of a free group on S generators. So we choose them, of course, there's a set of relations for gamma, so gamma will be isomorphic to this group. Yeah, gamma is any lattice is finitely generated and also finitely presented. So we can choose S and R to be finite. And this is important that we can choose them finite. Okay. Maybe I'll leave that and use this blackboard. So, okay. We'll write S as just some finite sequence of elements. I can write them, I can just draw them. S1, S2, Sk. And now I will choose some real numbers that will have nice properties. So we choose R positive, such that the ball of this generating set and identity, well, identity is always there, so generating set is in R ball, in the R ball. We'll choose delta positive, such that our group gamma intersected with B delta is just identity. And finally, well, I will have to choose an epsilon positive, such that, and this will be a condition which is a bit technical, but for every family of Si prime, such that the distance from Si to Si prime is less than epsilon. So I have a new tuple, k tuple of elements. All of them are very close to the old ones. Then I know that for such new tuples, every word in my relation evaluated on them is very close to identity. So W of S1 prime, S2 prime, dot, 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 Sk prime is inside B delta over 2 for every word in the set of relations. Okay, I'll put it up. Okay. Yeah.
Where do you find this like
SI primes, yeah, any elements of G. Actually, he said I will use color, so maybe I should do it. Yeah, so let me draw those balls. So B delta would be this. There is a smaller B delta 1/2 inside. And there is an epsilon such that whenever you find a new tuple of elements inside those small balls around the generators, every relation evaluated on them will land here in this small ball, right? Okay. It could also be identity, but we're sure that it will land here. Okay. So now if we have a lambda which is close enough to gamma, the following will happen. First, I will know that well, every element of gamma has to be approximated by some element of lambda when I restrict to BR. Right? BR is a bounded set. I can put it there as W. And I know that for everything in a bounded set, I will have points very close in lambda. So I for sure know that there exists S prime inside lambda. S prime equals S1 prime, S2 prime, SK prime, such that distance from SI to SI prime is less than epsilon. And also, using the reverse inclusion, since I know that the intersection of B delta with gamma consists just of identity, I know that my group lambda should not have any elements, for example, in B delta minus B delta over 2. So yeah, lambda intersected with B delta without B delta over 2 is empty.
Small relations are very small.
Yeah, small relations very small. And this, if you know, for example, well, you can work a little bit more, and we'll use that to show that this actually forces lambda intersected with B delta to be exactly identity because of no small subgroups property of real E groups. Okay, but we have, just from definition, we have those two properties. So, okay, so let's see what happens if we evaluate our relations on those words, on those elements. So by definition, those W evaluated on S1 prime, SK prime, they have to be contained inside B delta over 2, but at the same time they have to be in lambda because those are products of elements in lambda. And on the other hand, no small subgroups property of G. So this is property which says that if you have a subgroup which is contained in some small neighborhood of identity, then it has to be trivial. So we know this. This means that this intersection into is actually, intersection of lambda with B delta over 2 is actually trivial. Well, maybe I'll show you why. So if you have some non-trivial element inside the small ball, B delta over 2, eventually its powers have to escape this small ball because of no small subgroups property. So they have to cross this this set B delta minus B delta over 2, but this would contradict our condition 2. So the only possibility is that all the elements here are trivial. But this, in turn, this implies that lambda contains a copy of a group given by this exact presentation. Which is isomorphic to lambda. But then by Mostow, you can overshoot it and use super rigidity. But then by Mostow, rigidity lambda is a lattice.
That is right. Maybe you can think about it. Okay, sorry.
Mostow, no. Yeah, well, let's be just safe. For safety, Margulis. By Margulis, well, this means that this is a lattice. There is a copy of a lattice inside lambda, so lambda itself must be a lattice. Okay.
Wait, what exactly are you using to go from a group contains a lattice to it is a lattice? You're also somehow using this local discreteness, right?
In this lemma, right. I use.
Yeah, so it's this, right. So you prove, they give you proof it's discrete. Yes.
I still have two, so this will be impossible if it's not a lattice. If it's not discrete. Thank you. Yeah.
So
yeah.
Is the only place where you've used higher rank is just your gigantic hammer in the very
Yes. So the truth, I think this lemma works for anything that doesn't have SL2 as a factor, because here you could use Mostow Prasad, but this thing is not just any copy of gamma, it's a copy of gamma that lies very close to itself. So you could have used local rigidity, which goes back to Vey. So yeah, it's really a hammer, but it works.
But everything else is just general Lie theory.
Yes,
The only place you're using any higher rankness is just at the very end. That
Exactly.
In a copy close, then
Yes.
And he actually only uses Lie theory and then the small subgroup stuff. The rest is Lie theory.
Yeah. So yeah, we have used only no small subgroups and some local rigidity statement to finish the proof. Here, no. Well, okay. I see what you mean. That you're saying that they might be more relations, and
I guess you have to run this backwards. Satisfy more relations and use closeness. So I don't know.
yeah, I think yeah, this is a good point.
I mean, how does this account for dig filling?
This would not work for den filling because non-uniform lattices in SL2C do not satisfy local rigidity. Yeah, so we couldn't have used local rigidity here. Yeah, but you know what? I mean, maybe let's just use Margulis in both meanings. Super rigidity plus normal subgroup theorem. We can conclude. Yeah. So this is. I'm sure one could go around this issue with having even like larger quotient, smaller quotient, but if we use normal subgroup, then we're fine.
Maybe just because this is the Who would like to see a statement of, at some point, of superrigidity and or normal subgroup theorem?
Superrigidity should happen this afternoon.
Good.
Yeah, supervision, and we may put some of these statements in exercise sessions, just to knock them for
Okay. But we should remember to definitely do this. Okay. Right now, there's a magic black box and to be written down soon.
But okay, so since maybe, I maybe should have been more careful when saying this. So what I'm using here is that if you have a copy of a subgroup inside G, which is abstractly isomorphic to a lattice, then it really is a lattice inside the group. Okay, this is what we are using here. So this will follow from superrigidity, but it's just a special case.
And the normal subgroup theorem is saying that this thing, which was a priori just the quotient of a lattice, is in fact actually a lattice.
Yeah. Okay. So any other questions? Okay, so I want to just maybe write down the definition of what is a stationary random subgroup. Okay, so, well, we have this nice space with action of G, a space of subgroups with conjugation. And we would like to introduce some dynamical systems which can detect whether lambda was confined or not. And we know it's possible because of this blue box, but just using topological dynamics will not get us very far. To use higher rank dynamics, higher rank magic, we need to introduce some measures. So the best thing to have would be to have some nice G invariant measure on sub G, but there is no reason we should be able to construct such a thing. So the next best thing will be a stationary measure, and I will explain what this means. So from now on we fix a probability measure mu on G, and I will require this measure to be by K invariant. And I will want this measure to be smooth, absolutely continuous with respect to R. Okay, this thing is just for technical convenience. Bi-K invariance will be very important. So whenever I have such a measure on G, I can talk about mu stationary measures on any G dynamical system. So if G acts on Z is a let's say, continuous action. And nu is a measure on Z. We will define convolution of mu and nu. So we'll define it like this: integral of a function f on Z with respect to the measure mu convolution nu is just the double integral over G over Z f G applied to Z d mu G d nu Z. So this defines a continuous functional, and with some reasonable assumption on the topology of Z, maybe G is locally compact, you will define a measure in that way. Only thing that we'll be using all the time is that if nu is probability measure, then mu is and this convolution is also probability measure. So how much time do I have? 3 minutes. Okay. Okay. Maybe I should delete this. Okay. So now I can define what does it mean to be stationary for an action or a measure. So a measure nu on Z is mu stationary if nu is equal to mu convolution nu. And similarly, we'll say that an action is mu stationary if the measure is mu stationary. So G acting on Z mu is stationary if nu is. Okay. Now I can define a stationary random subgroup. So this will be just a stationary probability measure on sub G. And similarly, if I wish to talk about discrete ones, I'll just add discrete here and D here. Okay, and this will be the stationary random subgroup. And maybe a good thing to finish for today will be just a statement of a theorem that we proved with Cahig, which will imply Margulis's conjecture. So we can actually classify discrete stationary random subgroups of high rank groups. So I'll talk about ergodic measures and I won't have time. If you don't know what ergodic is, I will maybe explain it next time. But it means roughly that this doesn't decompose as a convex combination of another stationary probability measures. So an ergodic stationary random discrete subgroup of G is either trivial or a lattice. And well, a lattice, well, this is a probability measure, but what I mean by this is that it's supported on the set of conjugates of a fixed lattice. Yeah, so it turns out if you can prove this, and we already know our local rigidity lemma and characterization of being confined in terms of the orbit closures, you can deduce the positive answer to Margulis' conjecture. But I will present details next time. You can maybe think of it as an exercise, how to deduce it, and I will confirm if your proof were correct next time.
So this statement is for any mu absolute continuous?
This is true for any mu, as I wrote here. So Biker invariant and absolutely continuous. Yeah, you could weaken it a little bit, but more or less it's this. So mu stationary, yeah. Yeah, that's it. Thank you.